algorithms that are used in machine learning. We will discuss in this chapter 5 algorithms which are the most famous and some of the most effective learning algorithms. We'll start with linear regression. Linear regression is the most basic model which is used to, which is used for machine learning. So, for example, we have a labeled data set where we have n number of features and our x variable and our y variable, and we want to build a model which can predict the x variable, so the y variable based on the x variable. So one way to do this would be, we will first plot all the data points on a plot. So for example, here you can see we have plotted all the data points, and then based on the points we will make a line. Now this line, this red linear regression line, is so simply we want this line to be able to predict our y variable based on our x variable. So here you can see, if your x variable is 0, your y is going to be around 0, and if your x variable is 5, your y is going to be around, here it is showing 2.5. So you want this line which based on your x can predict your y. So you first plotted all the data points, and then you will make a line. Now this line is the best fit line. That means this line has the least error. So these data points, there are many lines possible, right? We could have drawn a line which went from -10 to, went steeper. We could have drawn a line which was more gradual. We could have made a line which, started, instead of starting where it has started, would have started at -5 of y and went from there, So why did we select this particular line? For that, we first need to understand two concepts. First of all, what is a line? This line was made by using a function which is y equals mx plus c, or in this case you can also call it wx plus b. So simply w or m, whatever you choose to call it, is the slope, and b here is the y-intercept. So what is a slope? The slope of this line simply shows what is the rate of change. So for a given change in x, how much change is in y? So for example, from 0 to 5 in the x variable, how much does, as the line goes from 0 of x to 5x, how much is our y changing? So our y is going from 0 approximately to 2.5, right? So the slope is 2.5 upon 5. Simply, slope is like your change in your change in y divided by change in x. So it is simply change in y given change in x. So that is the slope, and the y-intercept is simply what is the value of y when x is, whatever is the smallest value. If it's 0, 0, here the smallest value is -10. So what is the value of y when x is -10? It is minus, I think this is 6, or I don't know, -7. So using this, it creates a function y. So any prediction of y equals slope into x plus this intercept, because this intercept is always going to be there, right? It started on this value, then from there the slope was applied. So this difference between the x and y was always there, and then slowly the difference is, increasing, because the line is sloping upwards. So y is equals to mx plus c. This is the equation of this line. Now there are many lines with this equation, right? Somewhere your slope will be 0.5. For example, the slope of this line is 0.5. But why not make a line with slope 0.4? Why not make a line which y-intercept is, I don't know, 0, right? The reason is because of these data points. We want to fit these data points in the best way possible. And the only way to do that is that the distance between the data points and the line should be the lowest possible. So you want the error or the distance between the data points and the line to be the minimum. So how do we achieve that? We will use a loss function, right? And this loss function will calculate, so this loss function will be used to tell us like how much error is our model going through. and using this cost function we are going to find the optimal values for our w slope and b intercept variables. So to do that, what we are going to do is first we will calculate the loss. Now we are using mean squared error, so we will take each individual error, square it, and then take the average. Why are we squaring our error? Why are we squaring it? Why not take the absolute error itself? This is because if you take the absolute error, the negative error will cancel out the positive error. So for example, if you see the first data point, it is around -5, while the line is at about -7. So your error here will be -5 -7, which is -12. Now in your second data point, your data point is at, I guess, 6, or no, it's actually at 5, and your line is already at -4. So it's saying, okay, the error here is -5 -4, which is -9, but and so on. But for example, if you see the second large data point, which is at probably at 3, and your line which is at 2, what is happening here is your error is 3 minus 2 1. So this 1, when added with your -9 of the first data point, becomes 8. So -8. So your positive errors are cancelling out your negative errors, and what will happen is, due to this, a model which is not that good at predicting will say, okay, the negative errors are cancelling out most of the positive errors, so this line is the best, which is a problem. So we are using mean squared error. Due to the squaring, all negative errors are also turned into positive. So our total error, instead of being decreased because of the alternating between positive and negative, it will add up and we will get a total error. So now why didn't we use the absolute value of the error that I explained, right? But why didn't we use a cube instead of a square? There are a lot of arbitrary decisions, right? But mostly square is used because it solves all the problems, and cube requires more computation, right? Because instead of doing 5 into 5, now you need to do 5 into 5 into 5 to keep your computation less and also solve the problem. Plus it will also, again, because your negative -5 will be multiplied by -5, it will become 25. Then once again multiplied by -5 will become -75. Sorry, -125. So it's not solving the problem. In fact, it's causing it again. That's why we will go with squared error. You could also use, there are also other loss operations like binary loss which could be used, right? But we are using mean squared error. I already explained why. Now there are some problems, okay? In, like, why would anyone even use linear regression when you have more complex models? Why is linear regression still being used nowadays when you have models which are much better at prediction? It is because of overfitting. Linear models will almost never overfit. It is very rare, and so it is because of this property of the model that it is still used. Like, it makes errors more than other complex models, but the overfitting is rare. So for a case where there is a high chance of overfitting, people still sometimes go with linear regression. For example, here we have a regression of degree 10. This is not linear regression because this is not one line, this is a curve, right? So you can see here it's overfitting the data. It is trying too hard to fit every data point on the training set. Now while this is good because its training accuracy will be high, but once you give it a test, once you ask it to make predictions on the testing data, it will not perform well because it has literally copied the training data and just made a line joining all the dots. That's not going to help, because when you try to predict an actual data point, it could be different. In fact, there's a high chance that the data point will be different. You need to create a model which is able to perform well on unseen data as well as seen data. This model will perform very well on seen data, but the moment we give it a data point which it hasn't seen before, because it was so closely joining these known data points, it won't be able to predict that point well. So the reasons why linear regression is useful is because it doesn't overfit much. Also, the reason we use squared error and why it's so advantageous is because it exaggerates, it increases the error, the difference between the true target and the predicted one, right? So it makes the model become more sharp, try to reduce the error more strongly. Now let's talk about logistic regression. The first thing is that logistic regression is more a classification learning algorithm than a regression learning algorithm, right? The reason it is called logistic regression is because its formula is more similar to linear regression. We will explain, we will take a case of logistic regression on binary classification, but it can be used for multi-class classification as well, though it does not always perform so well in multi-class classification. So in logistic regression, we will still create a model, we will still want to create a linear function for x, which is wx plus b. But the problem is that this is a function that will go from minus infinity to plus infinity, right? If you go back to this line, if you add new values which are 15, 20, 25, this line will just keep going on. It will keep going on. It will never stop, right? It will go beyond what is possible. Like, there are some things which are not possible. Like, even if your house area keeps increasing over time, your price will never go beyond a certain point, because no one is gonna pay that much for a house. So, but linear regression will keep predicting higher values, because once the line has started on slope, it just keeps going straight. So that is one problem. And secondly, linear regression suffers from an outlier problem, which I will explain in the future. So now, how does logistic regression deal with these problems? It creates a curved S-shaped line. You can see here. So this deals with both problems. First of all, this cannot go till infinity, because you see, once it has straightened out, it's going to stay the same. So after a certain point, the predictions are 1, but they do not go to 2, 3, 4 numbers which are beyond possible, because a person can either 1, which is buy the insurance, or 0, not buy the insurance. 2, 3, 1.6, they have no meaning, right? Because if the person is buying the insurance, 1 should suffice. And secondly, the outlier problem. So simply here, the outlier problem that is possible is, suppose there is a data point at number 10, which you get now. So you populate it in the data, and it stands at around 5, okay, and you get a couple of such data points at 10 which stand at around 5. What this will do is, because you are getting so many data points of around 10 which are standing at 5, and our line ends at whatever this point, I think it's 6, what our model will do is, it will adjust the line so that those data points which are standing at 5 on our y-axis also are fit perfectly. Now if there are many data points over here, what we'll do is, it will raise the line, so the slope will become steeper. So it might start at the same point, or it may even change the start point, but the line will become different in trying to adjust those data points. So if you have these outliers of around 10, right, or suppose 10, and you have all these outliers of the value, for example, you have values which are coming on 10 at the y-axis, right? You have 2, 3 values. In trying to fit those two values up there, our model will change the line such that it is performing much worse on these actual data points here, in trying to fit those outliers to the line. This is a big problem, because it worsens the accuracy of the model. While the model is trying to fit those 2 points, it is messing up all of these 10, 15 points for the sake of those 2 points. Linear regression solves that problem because it straightens out after a while. So no matter how many outrageous or outlier predictions you have over here of, I don't know, 1, because it has already straightened out, it will not adjust itself in any way to fit those 2 points, because it is already fitted, right? So, and even if it does adjust itself, this area before it will remain untouched, because this S-shaped line straightens out after a while to the highest probability. It will anyways predict it to be 1. You don't need to, if this would have been a straight line, what would have happened is, it trying to fit those, it would have changed the slope. It doesn't, here it doesn't need to change the slope, right? Because the slope is not constant anyways. You can see this is not, the slope is first very low because the line is literally going straight, then the slope is steep as the line suddenly climbs, and then the slope is gradual again as the line stays straight. So by change, even if it does change the slope, it will not affect the records previous because the slope was never constant. Now this causes a problem as well, which I will explain. But first of all, let's understand how we got our sloped line. How did we get this S-shaped line? The way we got this S-shaped line is that we uh, used the sigmoid function. So the sigmoid function simply squashes all these values, right, to a probability, or squashes all target variables to a value between 1 and 0. So if you have values like 0 to 500, it will convert those values to values between 0 to 1. How does it do that? So it uses an equation, 1 upon 1 plus exponential raised to minus x. Our x is exponential raised to minus y, and our y is w into x plus b. So simply it says 1 upon 1 plus e raised to the negative equation of our line. So what this does is, simply suppose you have a value 500. So it says, okay, 1 upon 1 plus, so the e here is Euler's number, which is 2.71. So it says, okay, 1 upon 1 plus 2.71 raised to minus 500, if that's your answer. So your model predicted 500, which your linear regression model predicted 500. But you want to convert that 500 into values between 0 to 1. So it says 1 upon 1 plus 2.71 raised to minus 500. And we'll get a value of like 0.99 because of that. You can do the math for yourself, or you can check how the sigmoid function works. But what it simply does is, because of the 2.71 raised to this negative exponential, the value decreases to something like 0.9 something. So so it becomes 1 upon 1 plus 0.94, and 1 upon 1 plus, or it becomes something, yeah, so 1 upon 1 plus 1 upon 1.94 is approximately half or something. So it squashes all those values because of this negative exponential. Okay, so in logistic regression we don't use mean squared error. We maximize the likelihood of our training set according to the model. So what does this exactly mean? So what this means is, instead of minimizing the average loss, we are trying to make this line fit the training data, increase, like, we are trying to make a line which fits the training data better. There is a difference here, right? Because our line, in order to fit the training data, is here curving using the sigmoid function. So it's trying to just fit the training data, not minimize the errors. The main problem here was, if it just tried to fit the training data, it wouldn't even have shifted that much, because it would know that this is the maximum, this is the best it can do. It wasn't trying to reduce the errors, the distance between these points, that this line changed so much that the outlier problem emerged. Here it is just trying to do, it's just trying to fit the overall data the best. So if it has 10 points and it has fit those the best possible, and then 2 points are outliers, it will not try to change its curve or something, because it has fit the data as best as possible. Error is not its problem. 8 out of 10 points correctly fit is better than trying to fit those 2 points, and then your other 8 points are not fit that well. So maximum likelihood solves the outlier problem as well. So how, and another thing, likely, where we used to add up the errors when we were using linear regression, but when you're calculating likelihood, you multiply the products, you multiply the likelihood of each observation, because we are assuming that all observations are independent of each other. So instead of just adding, because likelihood can only go to a certain point, right? Error could be going till 500. but your likelihood of the data being can only be till 1, which is 100%. So it cannot go above that. So that's why we are multiplying. So if it is 1 into 1 into 1 into 1, that means your data has been fit 100% correctly. That's the best possible outcome. While if it is something like 0.5 into 0.5, your data has been fit only, like if your model is only able to fit half the data points and then half the data points, its accuracy is like really low, its likelihood is really low. So, and we will be taking the log of likelihood. The reason we are doing that is because we are going to the reason we are doing that is because uh, it is a because this if you can see the linear regression curve, it is always increasing, right? So we want the log to be used so that when we use this negative, where is that, yeah, this minus wx plus b, the reason we are using log is because so that these negative values cancel out because log of all the values between 0 to 1 will be something negative, right? So that's why we're using this negative value. Now let's get to decision tree learning. So what is decision tree? A decision tree is when you create a graph that can be used to, to guide you to make decisions, right? So here all these, this this cell, all these are known as nodes, okay? And this, this question which is yes or no, this is a branching, this is separating, it is converting one node into two different nodes, right? So this is the right branch and this is the left branch. So here yes is the left branch and no is the right branch, right? So usually what happens is, in each branching node a specific feature is examined. If the value of the feature is below a specific threshold, then the left branch is followed. You can see here the value of whichever this variable x3 is below 18.3. So then if it is yes, then the left node is followed, left branch. While if it isn't, then the right branch is followed, right? So otherwise the right branch is followed. And as the left node is reached, so we reach this node, we will make a decision about the class, right? So we got an example here. For example, x equals, in our example, x3 is equaling 15. Okay, it is below 18.3, so you take the left branch and then it will predict whether, what is the probability of y given that x was 15. So for example it will say 32. So okay, 30.32 out of 1, which is, less than 50. So the prediction is that your example is 0, is a 0 class rather than a 1 class. So in the beginning here, the decision tree makes only one makes the same prediction for any input. Then this diamond shaped cell is the first split, right? After this it will test this feature 3 if whether it is below 18.3 or more than, and then based on that it will follow up to one of the other leaf nodes. So the way this works is it uses an ID3 algorithm, which which simply finds the correct values for W and B, right? Our W and B there. So we have a W and B here as well, which will be used. So to find the values here, we are going to. So for example, so what is ID3? Simply ID3 is used to evaluate how good the split is. So for example, you are using this function, right? You're evaluating variable x3. Now when you're evaluating variable x3, why did you evaluate variable x3? Why didn't you evaluate, I don't know, variable x2? Why not x1? The reason we evaluate a variable, like in this case x3, and give it importance is because it has a high entropy. So what is entropy? Let's see, what is entropy? So entropy simply, so high entropy, we want low entropy. Okay, so what is entropy? Suppose if x is 18.3, there is a 50% chance of it being 1 and 50% chance of it being no, and if it is less, if it is more than 18.3, then also there's 50% chance of. So there is no use of asking this question, because anyways there was a 50-50 chance, and even now there's a 50-50 chance. So whenever the chances of both the categories are high, like in this case both are 50-50, then your entropy is also high, which means that your model will, this split is not helping the model in any way. Now instead, if your x3 variable, this question has, if said yes to, has a 75% chance of the result being no, if the result being 0 if the value is below 18.3, and a 20 and a 70 and a 80% chance of the result being 1 if the value is above 18.3, then your entropy will become low, because one category clearly is more favored after the split, right? Simply you want a model which can clearly, every split should clearly separate the records from one another. We want to be able to predict the ones and the zeros differently, right? So whether he bought life insurance or not, so is the age below 18 or above 18? So if this question, if this factor has actually any meaning, then those who are below 18 will have different answers when compared to those who have above 18, because we are trying to classify them differently. If they are still random, then you're not classifying anything, you're just you're you're back to stage 1. You're not going ahead, your classification is not improving. But if you are seeing a trend that okay, below 18 75% of the people didn't buy life insurance, though obviously below 18 no one does. So for example, below 25 no one bought life insurance, right? So you are seeing a trend. Now you can use this trend to predict the whether the person will buy life insurance based on age next time. So to observe these trends, we use this entropy.